Hello, and welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll be talking about computational grid generation. This is the first part of the third module of the class. In the previous class, we finished the introductory material. We talked about a mathematical survey and went over tensor mathematics and notation, linear algebra. Then we talked about classifications of general second-order PDEs. We looked at hyperbolic, elliptic, and parabolic systems. Then we looked at the wave equation, its physical meaning, and the solution. This was a linear partial differential equation. Then we talked about the diffusion equation, which dictates how maybe particulates are diffused through a fluid. We also looked at its analytical solution, but didn't derive it. This is also a linear partial differential equation. Finally, in the previous class, we looked and briefly introduced and reviewed the Navier-Stokes equations in their compressible form with an energy equation and some kind of gas model. This is mainly the type of equations we're looking at this class, which is a nonlinear set of partial differential equations. With the Navier-Stokes equations, or any type of PDE and its associated numerical solution, we have to discretize them. Why? Because we're solving them on digital computers. So we have to create a computational grid. We'll first look and define what is a computational grid in this class. Next, we'll look at an overview of the computational grids and classify different types. We'll talk about why we need computational grids and review the most basic example of discretizing a single term for use on a finite difference structured computational domain. Then we'll look at the sensitivity of these grids. We'll look at all kinds of grid metrics, and we'll talk about the all-important concept of grid independence studies and the parallelization of solvers on these types of grids. Finally, we'll look at a number of grid quality metrics. When you create a computational domain, it's important to look at statistics of the grid for all the cells and nodes and their connectivity, and derive statistics from the grid itself to see if you've made a good one that's appropriate for a numerical solution using computational fluid dynamics. Let's look at the most fundamental concept of discretization of these equations. Remember that our equations are generally written in the form of partial differentials, like on the left, which is the conservation of mass equation in the Navier-Stokes equations. Here, it's a compressible form of the equations. On the right, we have the similar form, but written in a volumetric approach. Finite volume solvers, which we'll talk about later in the class, typically use the formulation on the right. They're trying to conserve these quantities through each volume generated in the computational mesh. This is probably the most physically understandable type of approach for new users in computational fluid dynamics. And so, of course, there's advantages and disadvantages to both these approaches, which we'll discuss later. The approach on the left is actually used much more typically in the so-called finite element or finite difference solvers. Now, these equations are both in their continuum form. If we want to solve them in a discrete framework, numerically, on a digital computer, they must be discretized, and we have to have solutions to these equations everywhere in the domain for them to be valid and hold the boundary conditions. We can check their solution by finding the residual of the numerical solution. Recall in our first class when we talked about consistency of discretized equations and their solutions relative to the original continuum equation. Every computational domain in this class will be examined by either nodes or grid points, where these black circles, and their connectivity, which are lines between each circle. In this case, we've taken a one-dimensional domain and divided it in 3 nodes and 2 volumes or elements. We might use these terms interchangeably depending on the type of grid we're using. This distance between each of these nodes we label as delta x. This is the spacing or distance between each node. In 3 dimensions, of course, we'll have different deltas in different directions between each node. We also label each node with a number. For example, this might be node number 1, the second one might be 2, and the third node might be 3. We also have the connectivity here, which might say simply the connectivity is from 1 to 2, and the second connectivity might be from 2 to 3. So we can have lists of nodes and connectivity in files. This is how computational grids are stored within the computer. We might also, for now, and to discuss discretization, label each node as the particular node where we're trying to find the solution, is I, and the neighboring nodes is I minus 1 and I plus 1. Using a Taylor expansion, we can look at the basic finite difference approach shown by Euler. So if we look at one particular term, say it's one term in the continuity equation on the upper left for the finite difference approach, it might be partial rho u partial x. This is the continuum form of the equations. We can approximate this particular term using a Taylor expansion and truncation as a central difference approach. This is an approximation of the first order derivatives of rho u about I. So we would write rho of I plus 1 of u of I plus 1 minus rho of I minus 1 times u of I minus 1 over 2 delta x. There's actually an infinite number of types of choices of these discretizations, and they depend on the neighboring nodes I plus 1 and I minus 1, or even I plus 2, I plus 3, or I minus 2, I minus 3, etc. This particular finite difference approximation approximates the first order partial derivative of rho u located at I. You can see in the denominator we have 2 delta x. This is nothing but, if you look at it from a physical approach, of the change in the value of rho u from I plus 1 minus I minus 1 all over the distance, which is 2 times delta x. It's delta x plus delta x in this case. We can construct all kinds of different orders and types of partial differentials in the discretized framework. These are then put into the computer to find the partial derivatives numerically and solve the system of equations. It's really that simple. You can also do discretization using the finite difference approach in the time domain. Some of the homework in the class will have you try out a few of these examples. One might ask, why do we use a computational domain or a computational grid? Well, it all goes back to the first very point that generally people are not able to solve these equations, that is the Navier-Stokes equations with appropriate boundary conditions, analytically. You might say that your professor is too ignorant to solve the equations himself, and perhaps one day you might find some types of solutions or new analytical solutions so we can become less reliant on CFD. Or perhaps there's a totally new technique that nobody's thought of before. Your creativity here would change and revolutionize science. Now, recall that equations of motion, no matter the field, describe field variables for the problem that we're solving. And they're typically located, especially so in engineering for practical problems, locations x and times t. We live in a three-dimensional space and time is advancing forward. This is not any different than the equations of motion for the Navier-Stokes equations. Remember, our computers today are discrete. That is, they store specific values. In a sense, just like in quantum mechanics, energy has been quantized. Well, here all the information is quantized at discrete levels, depending on the number of bits of storage of the computer. So we can only store solutions at discrete locations of x and t. This is the core reason why we are performing discretization. We are not solving the continuum form of the equations. We're only solving the discrete form. This is a critical concept that many students struggle with. The struggle for many new users of CFD is asking, unlike other fields, why we need to solve for the whole solution in the entire computational domain. Well, it's because we need to solve the equation everywhere for it to be valid within the whole domain. It's that simple. Now, by using computers to solve equations, that is finding them numerically, the act of computational fluid dynamics, we are actually only solving the equations at discrete points x and t. After you set up your solver, your computational grid, and go through the solver process, the output of the solver, that is the numerical solution, is only known at the grid points. Alternatively, if it's a finite volume solver, it may only be known within each volume of the grid points. For example, in the previous discretization, where my cursor is in the middle between two grid points, the finite volume approach, which is a volumetric formulation shown on the upper right, would only know two particular solutions between I and I plus 1 and I minus 1 and I. Let's return to the question of what is a computational domain or computational grid. We will define a computational grid as a set of discrete points and connections between discrete points that approximates a physical and or temporal domain. The connectivity of the grid is implied or an explicit relation between a set of discrete points. An implied set might be for a structured grid, which we'll talk about in a few minutes. An explicit relation means a particular list of the connectivity between all the grid points, which are the particular nodes that connect all the connectivity, of course. Remember that equations are discretized so that the solutions are found at each discrete location or within each volume of the particular set of discrete points or connectivity. For example, we might have a physical domain. The blue area is where the fluid resides. The edges of the domain are where I'm moving along my cursor. We might take that physical domain and discretize it as a number of points. Typically, points are placed at corners of the boundaries of the domain. You can see in the computational grid I made on the right that I put grid points at each corresponding corner. I've also put a grid point between these 2 points because they're so far apart. This is a very, very crude approximation of the physical domain with a number of grid points. After I put grid points around the boundaries, I've put a number of interior grid points. Then I've connected them. The solver would need to find the solution using these grid points and their particular connectivity. This would be an unstructured domain. It would also be a very poor discretization of the domain itself. In this class, we'll look at examples of good computational grids and maybe not so good computational grids. We should also consider CPU time versus the number of grid points. The more grid points you add, the higher computational cost it will be to find the solution on that particular grid. Furthermore, the higher Reynolds number of the flow in general, the more computer time it will be required to resolve the flow. Also, the relation's not linear. On the right, this is explained in a figure. On the x-axis, we have the number of mesh points. This is just another way of saying the number of grid points in the computational domain. The domain here for testing is a simple square. It might have 21 grid points along each edge, 41 grid points along each edge, all the way to 101 grid points in each edge. The y-axis is representative of the computer time in seconds to find the solution using that particular computational domain. All other things in the simulation are the same. Now, we now vary the Reynolds number of the particular problem. This alters slightly the equations of motion. We have a case with Reynolds number of 400, 1,000, 3,200, and 5,000. And then the amount of computer time for each particular grid in Reynolds number are used to find the solution with that particular grid. They are connected by lines for each particular Reynolds number. As you can see, for the lowest Reynolds number, the amount of time the CPU takes in seconds to solve the problem using the corresponding mesh increases, of course, with increasing mesh count. So for example, for the smallest case, we have only a few seconds of time, which went up all the way up to 2,500 seconds of time for the particular CPU from 21 by 21 grid points to 101 squared grid points. If we increase the Reynolds number all the way to 5,000, the computational cost increases tremendously. For example, at 21 squared grid points, you have about 800 seconds of CPU time used, all the way up to 101 squared grid points at over 7,000 seconds used. You can see the increase in time used by increasing Reynolds number at each particular number of grid points does not grow linearly. One might wonder why that is, and we'll explain that later in the class when we talk about the particular solvers used. What you'll have to take away for now is that the more grid points you add and the higher Reynolds number of flow you have, either variable increasing, you'll find that you are greatly increasing the amount of time the computer takes to solve the problem. This translates into computational cost and, of course, finances. It could be that for some problems, it'll just take too much time and you don't have the type of computer resources to solve the case. So there's a balance here. This balance shows the computational cost increases with grid points. On the other hand, your accuracy of the solution increases with the number of grid points. You always want to add more grid points to resolve the flow and find a more accurate solution, And on the other hand, the more grid points you add, the longer it'll take. This is a balance you'll have to make as a user of computational fluid dynamics for solving problems. We'll have to develop some kind of metrics to decide when the solution is converged and independent of the grid. This is the idea that as you add more grid points, that the solution will not improve anymore, that it is grid independent. This is what we want to achieve in all computational fluid dynamics simulations. This is all detailed in a report called The Development of a Locally Analytic Prolongation Operator in the Two-Grid, Three-Level Method for the Navier-Stokes Equations. And here's the DOI number in case you want to pull it up. Let's look at some meshes. This particular mesh was developed by the NASA Ames Advanced Supercomputing Division using the fully unstructured Navier-Stokes 3D code from NASA Langley. The source is nasa.gov on NTRS. This is one demonstration of a CFD solver for a supersonic business type jet or demonstrator. In the upper left, you can see a picture of the nominal aircraft skin. Here's the engine, and this is the tip, and this is the end of the aircraft, in the most simplest of terms. Here, this picture is actually the computational grid with superimposed contours of the solution. You can see the engine inlet here and the engine exit. These are the tail here and the tail here, just so you can see that they're flipped across a horizontal plane. Now, what you see here is a plane extracted through the computational domain. And you can see that the particular lines are all the connectivity of an unstructured grid. It's colored by the solution. For example, this color here and these lines here might represent a shock wave which coming off the tip of this arrow spike for this engine. Where these little lines are all connected represent nodes. Now you can see that this particular computational domain has a lot of grid points and connectivity. What is interesting, it's only a plane of the entire computational domain. The actual computational domain might contain 100 million grid points and associated connectivity. Now, this grid is not a very isotropic grid or homogeneous. A lot of the grid points are centered around where the shock waves occur. So the solver has actually modified the computational grid as it runs to resolve shocks. Remember, shocks are discontinuities in the flow, and they have extremely large gradients. So the more grid points you put at a location of a shock, the more resolved solution you'll have. So they are willing to place more grid points in regions of high flow gradients, that is shock waves, to find the solution. It's not just shock waves that are being resolved. You can also see more grid points being put along this particular line and this particular line. What do these correspond to? Well, they correspond to the jet shear that's coming out of the engine. And that too is resolved. Why? Because it affects the shock waves, which become the sonic boom that propagates to the ground. Now, let's classify the types of computational domains. There's generally two. The first is structured and the second is unstructured. A structured mesh follows some structured convention. Typically, this is the so-called IJK index convention. That means that there's a list of grid points and there's no list of connectivity. Why? Because the connectivity of the particular domain is implicit and it's known to the user. It is assumed. There's no connectivity list in a structured mesh. For example, if I'm on a one-dimensional domain, my grid points might be labeled I equals 1, 2, 3, 4, 5. The implied connectivity, which is never written down for the one-dimensional structured mesh, would be 1 to 2, 2 to 3, 3 to 4, and 4 to 5. 5 grid points and 4 implied connectivity. This is the same case in a two-dimensional domain. You can imagine a two-dimensional domain, like in the lower left figure here, has a number of grid points. And in 2 dimensions, it would form a number of squares, for example. We might say that this is grid point 1, 2, 3, 4, 5, 6, etc., all the way around this side of the aircraft. If this is grid point n, then we would go one grid point away from the wall and call this n plus 1, n plus 2, n plus 3, n plus 4, etc. If we go 2 grid points away from the wall, we might call it 2n plus 1, 2n plus 2, 2n plus 3, 2n plus 4, etc. And we would go all the way to the maximum number of grid points in the j direction of the computational domain. It's that simple. And one can construct structured computational domains in this way just by having ordered list of nodes. Almost all finite difference solvers use these types of structured domains. There are certain advantages for structured solvers and solutions, which we'll discuss in this class. The second major type, of course, is the unstructured grid, which I might show in the lower right. We have previously talked more about these unstructured domains. Here again, you have a list of nodes, but we do not necessarily have to put the nodes in their order in any list or numbers in any particular order. We no longer have to say that in the lower right, this might be node 1, 2, 3, 4, 5, etc. But we can actually say that this is node 1, this is node 2, node 3, node 4. The order in the nodes no longer matters because we explicitly give a list in a file for the solver to read of the connectivity. For example, this might be connectivity 1 to 2, and then this particular node might be connectivity 2 to 43, and 43 to 54, and 54 to 26, etc. Out here, we might have node 17, and this might be node 48, 17 to 48. The whole list of connectivity simply describes the connection between the nodes. Now, typically, the mesh generation software, which we'll talk about in a few classes, and their algorithms, does have some kind of logical order for the way the nodes are constructed, but it's very difficult in complicated three-dimensional meshes to understand. This is why the list of connectivity is so important. There's other advantages for the solvers that use unstructured meshes. Typically, you can have much more complicated geometries in unstructured mesh versus structured mesh. Often, your order of your solution and your discretization can be much higher for structured type solvers. You'll have to balance and decide which one's appropriate for your problem. Typically, a solver can only use one type or the other. Finally, a multi-block mesh or grid might be a combination of overlapping or connected structured meshes or unstructured meshes. So if you have two structured meshes that are used by the same solver for the same fluid domain, for example, that would be called a multi-block mesh. It's not required that the structured meshes are exactly connected at their boundaries or not. This is the same for unstructured meshes. You can have multi-block unstructured meshes. This just means that there's different grids being used to find the solution. It's that simple. There's a number of unstructured grid element types. In 2 dimensions for unstructured grids, there might be something like a triangle or a quadrilateral. These are the most typical forms. In fact, there's many computational solvers that only use triangular meshes or tetrahedral meshes. Or there's many types of solvers that only use prismatic elements. These might be seen as the triangles and squares, and these are usually in 2 dimensions. In 3 dimensions, they would be represented on the surfaces or boundary of the domain. In 3 dimensions, things can become much more complicated. Excellent solvers will handle multiple types of volumes. They might be tetrahedrals, which are seen by my cursor, prisms, pyramids, the so-called wedge, or some kind of arbitrary polyhedral type. Many advanced research solvers typically only use tetrahedrals and prisms. You can imagine that you can decompose any 2-dimensional or 3-dimensional domain in triangles or tetrahedrals, and therefore you can actually decompose all these other types of elements in some mathematical way to the tetrahedral. This is why some solvers only focus on triangle or tetrahedral type solvers. You can also use an unstructured domain to try and find a structured mesh, and it might look like a bunch of 2-dimensional prisms or these hexahedrons. Now, it happens to be that these will still be unstructured meshes, and they would be incompatible with a structured solver. Remember, a structured solver will only read a list of nodes and not know anything about the particular connectivity, but is it implied to the solver. An unstructured solver could easily read a structured mesh and use an implied connectivity and treat it as an unstructured domain. So even if you have the same grid for an unstructured and structured solver, remember you should expect to have slightly different solutions because you are using a structured or unstructured approach, which has completely different discretization strategies for the equations of motion. We'll discuss this a little bit more later in the class. But right now, you can see all the different types of elements that you might generate in a computational domain grid generation approach. Let's talk about some of the common words used to describe a computational domain. That way you can communicate with other people about the domain you created. Typically, there's cells. A cell or an element might be a control volume in which the domain is broken up. This is usually a finite volume type grid nomenclature. In finite element, you might call them elements. In the finite difference approach, you would refer to the nodes. You're not so much concerned about the elements or cells or volumes. Some people call a grid point a node, so use them interchangeably. Grid points and nodes are typically the same thing in any type of solver. The cell center is simply the center of the cell. For example, in the triangular cell, in this case, it would be right where my cursor is in the middle of the domain. This is where the solution would be found in, say, a finite volume approach. An edge, of course, is the edge of a face, and a face is the boundary of a three-dimensional cell or element or volume. Now, zones might be groupings or sets of grids, nodes, faces, or cells. They typically refer to a multi-block domain. For example, I might have two zones, and they all consist of their own set of nodes and connectivity. Finally, we also have wall boundary zones. This is more of a solver-specific term. These might be where walls exist as a boundary condition. Fluid cells are where, of course, we're solving the computational fluid dynamics. We typically won't refer to these two types in this class. Finally, a domain is nothing but a zone, and they're used interchangeably too. A domain might also be a group of nodes, faces, or cells. Now, there's a number of types of meshes, and you might just refer to your computational domain in one of these ways to communicate to other people what kind of mesh it is. You might call it a tri-mesh, which is consisting entirely of triangular elements. A quad mesh will be completely quadrilaterals. A hex mesh would be completely hexahedral elements. A tet mesh or tetrahedral mesh would be only tetrahedrals. A hybrid mesh would be a combination of these elements in 2 dimensions and 3 dimensions. In 2 dimensions, these are typically triangles and quadrilaterals, and in 3 dimensions, it could be a combination of any type of 2D and 3D elements, which we've discussed previously. There's also very specific types of mesh. One might be a boundary layer mesh where you have many types of cells or nodes that are very compactly located near the boundary to resolve the turbulent boundary layer. We'll look at this theory later in the class for generating these. It can be pretty complicated to resolve a turbulent boundary layer and computationally expensive. Finally, there's the non-conformal mesh, and this might be a mesh where the nodes do not match the particular interface. These are used typically in immersed boundary approaches, which we will not be discussing in this class, but this is also an emerging area of research in CFD. Let's talk about the idea of grid independence and grid independence studies. Basically, grid independence means that the solution is independent of the grid. If we add more grid points, the solution does not change. If we rotate the grid points in some way within the solution domain, the solution does not change. It is independent of the grid. It is very difficult in computational fluid dynamics to show that your solution is grid independent, but it's critical to prove to other people that you found the correct solution. Let's look at one particular case. Let's pretend that I have a cylinder in a supersonic crossflow. My initial domain might be shown in A. This is a strange domain, and we'll be talking about these kinds of meshes in this class. The flow might move from left to right. When we find a solution, we see that there's some turbulent wake behind it, and we might go in B and add more grid points around the cylinder in the wake. Well, we also notice that there's a shock wave in front of the cylinder, and we go in and we might add, using the solver itself, or a grid adaptation approach, or just add them manually, more grid points to where the bow shock is located. In this case, we've added more grid points and regions to resolve the shocks and wake and boundary layer independently. We would keep adding these cells and shocks until the solution does not change relative to the previous solution that used less grid points. Comparing these two solutions, if they're the same, then we would consider that it is a simple study for grid independence. We can see one contour of this particular flow field in the lower left corner. Here we have the black line, which is the shock, the bow shock. The flow moves left to right, and we see pressure contours forming around the cylinder. There's the turbulent wake, and then here are shocks too. In this case, there will be a lot of grid points located on the shocks and the wake and the boundary layer around the cylinder, and a lot of grid points along the bow shock. We would also need enough grid points to resolve these gradients of all the pressures and velocities around the cylinder. One difficulty, of course, of this whole approach is knowing where to put grid points for the shock in the first place. Often you don't know where the shock is located or where the wake will be exactly, or any other type of flow physical phenomena. Therefore, it's almost an iterative process to find grid-independent solutions. Today, modern solvers try and do this automatically, but it is still an emerging technique. And it's often better for the user to try and create a high-quality computational grid before the solution is even started. Remember, you want to use the least number of grid points possible to find the grid-independent solution so you can reduce computational power. But you don't want to reduce the grid points too much, or else you won't be resolving the flow field features like you see in the grids A, B, and C. The details of these particular grids are shown in the right-hand corner for different numbers of grids. They call their grids 1, 2, 3, 4, and 5. You can call them anything you want. Numerically ordering your grids with a problem name might be appropriate. Here on the right, they've simply increased their cell counts by powers, and they have come up to a solution where they find it to be grid independent of approximately 262,144. They would compare this last solution with grid number 4, and if the solutions are different, then of course they do not have a grid independent solution. If solutions from grid 4 and 5 are the same, they would consider them to be grid independent. Let's look at this so-called grid independent and sensitivity study. We'll define grid independence as the numerical solution which is independent of the computational domain. That is, if I add more grid points, I rotate grid points, I move grid points, that the solution is remaining the same. How can you compare them? Well, you have a digital computer. You can have two solution files or databases from a solver with the corresponding computational grids, and you can simply compare the two. If they are the same, then you have a grid-independent solver. You might use more advanced mathematical methods to prove this to the user, at least numerically. Remember, if you double the number of grid points and the solutions are the same and they converge, then you do, of course, have a grid-independent solution. Rotating the grid or using another type of grid should also result in the same solution. For example, if you have a grid and you're able to rotate it within the fluid domain and you find the same solution, then you have a grid-independent study. Finally, if you perturb the grid points, that means if you have a grid and you move every tiny little grid point within it a little bit epsilon in either direction, enough to affect the solver, but enough to retain the same solution, you might also say that your grid is not sensitive. And that's very important. You would not want your solution to be sensitive to the grid. So by perturbing the grid points within the domain without moving the boundaries and finding the same solution, you have a grid insensitive solution, which is another important test if you really care about the validity of your computational domain and your solution. Now, if you create a computational domain, and to remind you, there's many types of software to do that, and we'll be looking at one particular software in this class that generates computational grids, you'll have to look at the statistics. So in the grid generation program, you can find a statistics report, and this report will tell you the number of cells that have perhaps unfortunate statistics. Statistics are very important for looking at the quality of the computational domain, and people might ask you about your computational domain statistics. One perhaps is skewness, which is illustrated in the figure on this slide. You can see that there's two particular centers for these two cells or elements. Each one has connectivity, and they share 6 nodes and 1 face. Now the angle, if you draw vectors from the face to the center, might create an angle theta. This angle theta is defined as a skewness. Ideally, you would want the skewness to be 0. You can imagine if your skewness is very large, like 85 degrees or higher, then there's a large skew between the two faces, and the solver will have trouble creating a solution there. Many commercial solvers add in a lot of dissipation so that artificially to find solutions. A research solver that might find a high accurate solution might crash if the skewness is too high. That's true for all these metrics. So after you create your computational domain, try and look at different metrics and reduce the skewness angle along with these other statistics. Let's look at some more of them. Another one is the angle relative to boundary face. So here in the lower figure, we might have a wall along our vehicle, and there might be some cell center or the grid point connectivity to the wall grid point makes a large angle relative to the wall. We call this the wall angle, typically. Now, if the wall angle is very small, like 10 degrees, like in this corner or here, then, well, not here, it would actually be the other angle to the left. In theta, you would want to be near 0. The wall angle for a finite difference grid you would prefer to be like 90 degrees between the wall and the line going to the grid point away from the wall. If this is too small or too large, depending on the way your definition is of this particular angle, then you cannot hope to resolve correctly the turbulent boundary layers. And this is because solvers prefer, which we'll talk about later, a computational domain which has wall angles close to 90 degrees. You might also look, and especially for finite element and finite volume approaches for unstructured meshes, cells which have some sort of face, so-called face validity. You can see from these two cells that one, the solver might have a particularly good time handling, and the other one, unfortunately, bad time. Another type of cell example would be, in this case, between two computational meshes for unstructured grid. This one is nice and even. Each face of the cell is roughly the same. Their volumes aren't changing from cell to cell. An example of a bad cell quality metric would be on the right. These are both exactly the same list of nodes and connectivity. The only difference is that the nodes are put at different places. Excellent computational grid creation software will try and create so-called cells which are good and try and improve their metrics on the left versus ones on the right. You can imagine that the computational solver phase of CFD will have a lot more trouble handling this type of cell. So it takes a lot of practice as a computational user making grids to make quality cells versus non-quality cells. Today, a lot of this is done automatically, so you don't have to go in and manually fix these cells. But if you're generating a mesh of billions of cells over, say, a landing gear, which is very complicated, of an aircraft, then you might encounter these bad cells created automatically by the grid generation program. You'll have to go in and tell the solver to try and fix them automatically after it identifies them through statistics of different types, or go in and actually have to manually adjust them yourselves. For example, in this bad cell, I could collapse this inner volume or element by connecting nodes and merging the nodes here and here as an example to improve the metric. The skew angle between these two nodes is way too small, and that will make the problem numerically ill-posed, and the solver might diverge from one bad cell. Another example might be volumetric changes. In an unstructured domain, we can see two examples here of so-called good cells and bad cells. The cells around the middle one all have relatively the same volume. The cell in the middle is much too small. Relative change in volumes of elements or cells that becomes too large makes the solver unstable, and the solution will not be as good. You want to have a gradual change of the volumes of each subsequent cell. It might be plus or minus 10% of the volume of the neighboring cell might be a good metric. 100 or 200% volume changes would probably be bad and make your solver unstable, perhaps. In the finite difference approach, this is also true. For example, from grid point 1 to 2 might have a distance of, say, 1. And from grid point 2 to 3, it might have a distance of, say, 10. This would be a factor of 10 change. This would be much too high for a stable finite difference solver. Typically, you would look to around 10% changes between distances of neighboring nodes in a finite difference grid. These are just rules of thumb. It'll be different for every type of solver. So you'll have to be familiar with your solver that you're using to understand what kind of grid metrics they used and are acceptable for the solution to be stable and give you something that's physically meaningful. There's another type of cell, which is the so-called chevron cells in unstructured meshes, or finite difference meshes. You might see two examples on the left. Typically, you would want the vector between cell 1 and 2, the center of the cell, to be relatively normal to the cell face and go through the cell face between the two cells. In a chevron cell, the vector might not go through the two faces. This is often critically important for finite volume solvers. This is not necessarily the case for a finite element solver. But for a finite volume solver, you're really looking to calculate fluxes from each cell center through the faces. If the flux is not going through the face, that's sort of an unphysical concept. Those solvers can handle this, especially in the finite volume solvers. It is not really a physically plausible explanation. Warpage of cells is usually for finite volume type of grids, unstructured grids, and finite element types of grids. It could be that the face of a cell might have 4 grid points, and it's flat in a plane. Now, it's possible to add more grid points to a particular cell and move them into or out of the page in this case, and you might get something looking like on the right, where you have a warped cell, that it doesn't make it necessarily a flat face. Typically, you would want your faces of your cells to have as little warpage as possible. Now, in some solvers, this won't be a problem, but in most computational fluid dynamics solvers, it is. And this is something you should avoid, and often your grid generation program will do this automatically. If it can't, it might give you some warnings or problems in the grid, and you'll have to regenerate the entire thing. If not, try and fix this problem. Let's look at a really great example of a computational domain. This one is from the website Another Fine Mesh, which is a blog generated by the Pointwise company. Pointwise is a company that makes standalone, high-quality computational domain software. Here they used a basic tube and wing type commercial aircraft where the orange part is the fuselage, and here, of course, is the wing. There's some slats and flaps on the wing, respectively. What they're showing here are surface grids, which are unstructured and colored by different faces or planes or parts of the grid. For example, this represents the wing tip. There's no winglet on this aircraft. And if you're able to see, you can see the connectivity and grid points along the surfaces of this mesh. This is typically called a surface mesh. When creating a mesh, you would initially define the surfaces and make them watertight. You make a watertight, without holes that is, domain of the fluid. On all the surfaces of that domain, you create surface meshes. From the surface meshes, you create an interior volume mesh. We'll be trying out this process multiple times in this class, but you can see, if you're able to see this on the compressed version of the video, there's also these grid points out here in the white area. This represents a symmetric plane that cuts the aircraft in half. Why do they do that? Because there's a steady flow about the aircraft which they're trying to find, and they're using a plane of symmetry of the solution, which is implied, that's being forced through a boundary condition. This will reduce the number of grid points by half and greatly reduce the computational power and time it takes to find the solution. When I see a mesh like this, I know it's high quality, and the Pointwise company makes a very high quality product with really good meshes if they have a trained user. Let's look at a particular mesh from NASA, which is unstructured and used to, of course, resolve a shock. This is called, through their method, through a solver technique, the anisotropic shock capturing adaptation methodology. You can read about this more at this NASA technical report server link, which I've showed down here at the bottom of the page. You can see that the original grid is shown here in A. We have an unstructured tetrahedral domain or triangular domain, and they've placed many grid points where the shock is. So the solver initially found a shock, and it added more grid points and altered the connectivity to resolve the shock wave. Look at how many grid points they have along where the shock wave occurs. That is because there's a huge flow gradient at the shock wave location. That is, pressures, temperatures, and velocities are very, very large at the shock wave location in a viscous simulation. Now, if they go in and zoom into that red box in part B, you can see that these cells have very, 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 very small angles. The skewness quality is really bad, and the solution quality, therefore, is not very good. They've gone in and used an algorithm, which they developed and discussed in this paper, to alter the cells so that the lines are orthogonal to the shock wave direction. This improved the solution greatly and allowed them to both cheapen the simulation computationally and resolve the shock more accurately. You can look at these types of solutions in this paper to understand it at a deeper level if you wish. But you can see there's the so-called good, the original grid, with its really, really bad discretization and mesh in the shockwave region, and an example of a much better grid using just triangular elements. You'll notice that their solver is triangular or tetrahedral, and therefore they have to put in these types of elements. So they do retain a skewness angle. The difference is they've structured the triangles within the shockwave region, and that's the best they can do with this type of solver. The only thing they could do better perhaps is add more grid lines in the direction that I'm moving my cursor to reduce the skewness angle, but that would greatly increase computational power, and their solver is robust enough to handle these small angles. Let's summarize and talk about what we discussed today. We introduced the most basic concepts of grid generation. Remember, in a computational grid generation process, you need to find some fluid volume with no holes, that it's watertight, define the surfaces, and create a surface mesh if you're in 3 dimensions. If you're in 2 dimensions, your surface mesh is the grid that's used by the solver. In 3 dimensions, once you have your surface meshes with grids and connectivity, then you create a volume mesh interior. This might involve advancing methods where you have boundary layer refinement, wake refinement, or trying to put grid points around shock waves. This is a very detailed process that can really only be learned with experience, which we'll be trying in this class so you get a taste of what it is. We also define grids and what they are and how they're used. Remember, there's structured and unstructured grids. Those are the 2 major types. Structured grids do not have connectivity because it's implied. Unstructured grids do have connectivity, and they can exist of many types of elements. We talked a tiny bit, and for only a few minutes, of what a good computational domain looks like and what maybe a bad one is. You'll learn this through experience mostly only, but throughout this class we'll look at more examples. We also talked about the so-called sensitivity of grids and the grid-independent studies. These are critical for showing that you have a true solution of the discretized equations. The solution must be grid-independent. If the solution is grid-independent, then it is not a physical solution of the equations of motion. Finally, we looked and went through a bunch of quality metrics for you to judge with your grid generation program to see if you have a quality grid. You should report these in research papers if ever writing a paper on CFD, or in presentations of CFD if you're working in a company. We also talked about how to find grid independence and how adding more grid points in a simulation greatly increases the computational cost. It is a nonlinear cost you're paying for adding grid points, especially in 3 dimensions. Finally, we just looked at a few quick examples of what these grids might look like. But remember, you'll see many more through these class, and you can find many online that are really great. Next time, we'll be talking about structured grids in particular and more examples of structured grids, so you'll get a better feel of what those are. We'll talk about why structured grids are wonderful to use in research and programming and for solutions. They have many advantages over the unstructured technique. They also have many downfalls. We'll basically point those out too. We'll also show some more finite difference examples. We'll talk about the implied connectivity of structured grids, and we'll look at some algorithms for generating structured meshes. Some can be as simple as a few lines of MATLAB or Fortran or C. Other times it can be very complicated and almost as complicated as creating an unstructured mesh. And they are certainly more time consuming for you, the user, to create a structured mesh than an unstructured mesh. This is one reason a lot of companies and research organizations have moved to unstructured meshes, because they're easier to create for complicated geometry than a structured mesh. Finally, we'll talk about the Jacobian and structured coordinate transforms. Thank you very much for your time today. I'm your professor, Steve Miller.